Welcome to the second Houdini tutorial from 9between, and in this tutorial I'll be showing you how to create these Doctor Strange inspired portals. Now, it's going to get quite Vex heavy, so my apologies if it becomes long-winded or confusing, but let's dive in. So we'll split it into a few steps. Firstly, we'll create a circle that has some normals according to its tangent, and then we'll flip some of those normals to face inside the circle. After that, we'll add some motion to it, and then using that motion we'll generate velocity to drive a particle system. Then finally we can render that particle system out. In Houdini, we can begin by dropping down a geometry node. Dive inside, delete that file node, and then drop down a circle. And we will be changing this primitive type to a NURBS curve. And that's the only setting we really need to change in there. The only other thing is that we won't actually be using the mesh, but rather just the outside points. So to avoid being distracted, we can just set this to wireframe, and now we just have this ring. Next, drop down a resample. And instead of using maximum segment length, we'll be using maximum segments. Set this to 100 for now. And now we would like two attributes to be output from this resample node. Firstly, a tangent attribute, and secondly, a curve U attribute. This tangent attribute we'll be renaming to N. And the reason for this is that Houdini has a display normals function over here, and it displays the N attribute. So if we set our tangent attribute to N, we can now see our tangent attribute. And we will be using this to drive our velocity for our particle system later on. So next, we'll drop down our first attribute triangle. And just call this one mult for multiplier. And in here, we will say @n times equals channel float. And just call this channel float mult or multiplier. And then create this parameter and set it to 2 for now. Just set your display flag, and now we can see that all of these normals have been adjusted. And if you drag this, you can see exactly what it's doing. So back to 2, and now we can move on to our next attribute triangle. We'll be calling this attribute triangle reverse. And the reason for that is we'll be flipping around some of these normals to face inwards. And to do this, we will say if rand @ptnum times @frame less than 0.1, do the following. Now, just to quickly explain this, we're saying if a randomly generated number every frame based on our point number is less than 0.1, then do the following. So this will return about 10% of all of our points. And in our if statement, we will say matrix 3 rot for rotation equals ident, which gives us a identity matrix. And then we can say rotate, which is a function. And then in here we can say rot and the amount that we would like to rotate it, but we need to convert it into radians. So in here we'll say 15 degrees, and that will be converted to radians because the rotate function uses that. And then the axis that we would like to rotate this around. So we would like this to rotate around the Z axis. Over here, you can see it's the one that goes through our circle. So we can say 0, 0, 1, and close this off. Next, we can say @n times equals rot. Now, at every frame, some of our normals will be flipped to face inside our curve. However, we still haven't added any motion that you see in the actual effect. So that's what we'll be doing in this next wrangle. So drop down another attribute wrangle and call this one motion. Now we'll bypass our reverse wrangle for now, just so that we can more clearly see what we're doing in our motion wrangle. Alright, let's begin by creating a float called flare, and we will say fit01, and inside of that we will say absolute, and inside of that we'll say sine, and finally inside of that we will say at time. Now we would like to fit that between 0.5 and 1. And then we will just use this as a multiplier. So at n times equals flare. And then if you play this back, you'll see what it's doing. It's gently flaring. So to explain what's been done here, we have this sine curve. And a sine curve looks like this. It goes from 0 to 1 to -1 back up to 1. And that gives us a really smooth motion, but we don't want it to go below 0. So what we do is we use the absolute function. And absolute flips all of the negative values to positive. So now it ranges between 0 and 1, and it only goes between 0 and 1. And so if we go back here, we can see that that's exactly what we've done. We've made the absolute of a sine curve that is driven by time. So as time progresses, it goes along the curve. Now, this fit01 compresses those values, so they don't range between 0 and 1 anymore, but rather between 0.5 and 1. And so, as you can see now, that just gives us that flaring effect. So, although we have very basic movement with this flaring, what we don't have is movement along the z-axis, which is really what sells this effect, because without it, it's very flat. So that's what we'll be doing next. So back into our motion wrangle, we'll just say Alt-E to bring up our string editor, and we'll create a few things. Firstly, a float called xdir for x direction, and this will be a sine-based variable. So at time multiplied by 3 outside of the bracket divided by 2. And very similarly, we will do a ydir for y direction, except this time we'll be using cosine. At time multiplied by 3 divided by 2. And then we will create a vector. And this vector will be using the directions that we created earlier. So we will call it vector direction equals set xdir, ydir, and 0 on the z-axis. Next, let's create a random float. So it'll be a float that we'll call r for random, and we will fit this between 0 and 1. It'll be a random value based upon our at pt num multiplied by at frame, so it changes every frame. And then we would like it to be compressed between 0 and 1, 0.1 and 0.5. Close that bracket. Next, we'll go at n, and now we'll be using something different. We will say plus equals cross at n, comma, direction multiplied by r. And if we apply and accept, this should work. And if you play it back, you'll see what that's done. Now, it might not be clear at first, but if you look at it from the side, we've done something pretty interesting. We've created motion along the z-axis. Now, what we've done here is we've used the cross function to take the direction that we made earlier on, called direction, and we crossed it with our current normal. And to understand what crossing does, and so as you can see, if you multiply one value by another, so if you multiply this x value over here by your z value over here, then you get the value that's perpendicular to it. So you get this y. So x times y equals z, y times z equals x, z times x equals y. So the way that we can use it over here is that we're creating values that are perpendicular to our n value and our direction. So that gives us these values that move in and out along the z-axis. So if you found any of that confusing, or if you found that my explanation was lacking for any of the VEX, then you can go to our blog post at our website, and over there we'll have in-depth discussion about all of the VEX code. It'll also be all written down in text so that you can copy and paste, compare it to your own code. So check it out, I'll leave a link in the description. So let's continue. Right now we have more interesting movement. It's no longer linear, it's now moving on more than one axis. However, we still don't have the actual effect that makes the portal look like the portal from Doctor Strange. And the portal from Doctor Strange has a bright point that is leading, and it gradually fades off. So what we need to do for that is use our curve U attribute to see where along the curve we are. And let's just visualize this curve U attribute so that we all know what we're talking about here. So activate visualization, right click on it, and then say add visualizer marker. And in this attribute box, we'll say curve U. Close that, and now you can see our curve U attribute. It's an attribute that goes from 0 to 1 depending where on the curve you are. So it'll be 0 at the beginning, and it'll increment upwards to 0.1, 0.2, 0.3, 0.4, and so forth until it nears 1, and that'll be the end of the curve right next to the beginning of the curve. So that's great because we can find exactly where along the curve we would like certain things to happen. So let's bring this back up, Alt-E. And now let's create a float called timer and make that equal to 2 times at time minus at curve U. Next, we will say at brightness equals channel wrap, and we'll call this timing wrap. Timing underscore wrap, and we will drive this by our timer. Next, we'll say at n times equals fit01, say at brightness, comma 0.4, comma 0.6, semicolon, apply and accept. Now we just need to create that channel wrap. We go back to our mult and push this up to 5. It will now be quite easy to see what's going on here. However, when you play this back, you'll see it's the reverse of what we want to happen. So as you can see, we have this bright area which fades off. However, it's fading off in the wrong direction. As you can see, it's as if it's sharp over there and fades off that way. However, we want it the other way around, so it's bright here and it fades off this way. To do that, just put a minus in front of your timer attribute, and that'll fix it. So now when you play it back, it flows in the right direction, and it now resembles the effect that we're going for. So, finally, what we'll be doing is adding extreme noise to this, because it's very easy to see what's going on in this effect, unless you add some noise. So we'll say at n times equals rand at pt_num, so it varies per point, at time, and then we'll just say at v for velocity, and this will be the final step. This is where we take our n attribute and cast it to our v attribute, which will be used in our pop network. So at v equals at n, and that will be all that we will be doing for our motion. Now, you may look at this and think that that noise really just kills the effect, because now all of that work that we've done is lost. However, if you re-enable your reverse node, go up to your resample node, and change this to 2000, you can still see exactly what's going on. And you can still see that bright point that's speeding around along the curve, and you can still see this movement along the z-axis. So it's all still there, it's now just quite noisy. And that really masks the effect, but makes it more believable. So this is great, but we still haven't done anything to actually create an effect. So let's actually make use of these normals in a pop network. So drop down a pop network, connect your attribute wrangle for motion into the first input, and let's switch off display normals, jump back to frame 1, put our display flag on our pop net, and then jump inside. Now on this pop source, we would like emission type to be changed to points. Next, we're not going to be using constant birth rate, so set both of those to 0. And on impulse count, we'll set this to 10,000 for now. And we would like our life expectancy for these particles to be very low. So set this to 0.05 seconds. Set life variance to 0.05. And then duplicate this pop source and plug it into this merge node. Now we have 2 of these, but the second one, we would like to change its impulse count to 100 and set its life expectancy to 1.2 with a life variance of 0.2. So now we have particles that are dying very quickly, and that's the majority of them, but we have some particles that are flying off that take a long time to die. So that adds some interest to it. Next, we'll drop down a pop wind and put it after your merge node. Set air resistance to 0.5 and amplitude to 1. And then drop down a ground plane and a merge node. Plug that ground plane into your merge node, swap these inputs, and then just set your ground plane's position on the y-axis to -1 so that it doesn't intersect our circle. And then the last step will be to drop down a gravity force. And this gravity force, we won't be using the default of negative 9.8 meters per second, but rather just -1. Jump up. And if you play this back, you'll see that it's quite sparse, and that the effect isn't actually that definite. And to fix that, we can just go to simulation outside of our pop network and set the sub-steps to 5. And these sub-steps will increase the amount of particles, but also if you decide to introduce some motion, like so, by putting a transform node before your pop net, and then giving it some animation, so we can just do that quickly, create this transform, and let's just keyframe our translate at frame 1 by holding Alt and clicking on translate, and then go to frame 96, and we'll just move it along the Z-axis. Alt-click there, and then go back to our pop network. And you'll notice that it does take quite long to sim, and I will show you how to cache this out shortly. And that's simply because of the substeps and the increased number of particles. So now you can see it moves like so. And what would happen is if you did not increase your substeps, so we can do an example of this. If we set this back to 1, you'll notice banding. So just keep note. Now if we play this again, you'll see banding. It appears as if there's 2 rings, and that's simply because we don't have enough substeps. So set these substeps back up to 5, go back to frame 1, and I'll show you how to cache. So drop a file cache node over here, plug your popnet into it, and then we'll go choose a location. So I'll just go to my main drive, create a file called portal tutorial, and then inside here we'll just say portal cache dot $f, and that's important so it saves every frame, dot bgeo dot sc, and that's the file type that I find best for saving and caching. So we'll say accept, and let's just change this frame range over here. So firstly click on that and change f end to 96. We'll just cache out 96 frames. and then we can say save to disk. So once this is cached out, we can just say load from disk, and that'll stop it from resimulating, and it'll just call whatever saved to disk. Next, we need to just remove this ground plane, so drop a delete node. And where it says pattern, set that to star, and that'll delete all primitives. Next, drop an attribute wrangle, and this will be our last wrangle. Call this one shader. Hold Alt-E to bring up our string editor. In here, just say @emit_int equals @brightness times channel float, and call this channel float mult for multiplier. And then we'll say float fader equals fit01 at time, comma 0, comma 1, and then @emit_int times equals fader. So what this does is it initializes this parameter called emit_int. Now emit_int Houdini recognizes because it is used in the principled shader. So what we can do with this is assign it a value, and Houdini will automatically pick it up in the shader. So emit_int stands for emission intensity, and that's basically the brightness or the light that it emits. So each particle will now be emitting light based on this emit_int attribute. Next we say float fader, and we fit it between 0 and 1 based on time. So at frame 1 it will be 0, at frame 24 it will be 1, and it will fade upwards. So we have this fader so that our effect fades in. So it starts dim and it gets brighter. Next we'll say @opaque for opacity, and this is another parameter that the shader recognizes. And this is just the opacity, so whether it's see-through or not. So we'll say opacity equals 0.025. We can say @opaque times equals fader. Then we'll say @emit_int times equals absolute @age minus 1, so that we can take the age of a particle and, depending on how old it is, adjust its brightness. So the older a particle is, the dimmer it will become. Finally, we need a way to give this color. So we'll say v @emit_color, and that is another parameter that's recognized. And we have to say v @emit_color, or else it won't recognize it as a vector, and you'll just end up with a black and white color coming out of this. So we'll say emit_color equals channel ramp, and just call this CLR_ramp for color ramp, and we will drive this by @age, and we can say apply and accept, and create these parameters. Firstly, set your multiplier to 1, and we can't really use this type of ramp for color, so we'll go up here to this gear, click it, and say edit parameter interface, and you'll see all of these existing parameters. Go down to color ramp, and where it says ramp type, change that from float to color. Apply and accept. And now, at this first point, let's just give it a color. So we'll give it a champagne color. And then this one over here, we'll give it a blue color. And fade it down a bit. Just make it desaturated. And that should be alright. So finally, we need to actually see this in a render. To do that, jump up a level, and we'll rename this to Portal Geo. Next, find a view that you like, so perhaps from the side or the top, and I'll just do it at this angle over here. Hold Control and click on Camera, and that will create a camera at that angle. So now there's a few things that we need to do before we can render. So go to your material palette and drive a principled shader from this one side to the other. Click and drag it there. And then go to your object level again in the network view. And over here, go to render. And that principled shader that we just dragged over, select that. Next, we go down to sampling and activate geometry velocity blur, and that will allow us to have some motion blur to this. Then go to geometry, and this point scale is how big our points are when they get rendered, because currently we just have a whole bunch of points that Houdini doesn't know what to do with. So how big should they be? Well, 1 is quite big and it'll just show up as a whole lot of blobs. So just drop this to 0.75, sorry, 0.075, and then we can go to the render view and select object camera 1 and then say render. And what you'll notice is it looks as if it's working, but upon closer inspection you'll notice that we don't have velocity, or motion blur rather. So to fix that, go over here to your object level and go to out. Select this mantra underscore IPR and then go to rendering, and where it says allow motion blur, activate that. Now you'll see that we have these streaks based on motion blur. And you can adjust this if you go over here to your render view where it says OBJ Cam 1, and this next to it, open camera parameters, and then click on sampling. You can set this up to 1 if you like, and what that'll do is it'll increase the length of the streaks. If you're familiar with photography, you'll understand that this shutter time is how long the shutter's open, so more light is allowed to enter. So we'll just set this to 0.5. That's just for interest's sake. And close this. And as you can see, it's rendering quite well. And we have our champagne color over there, and as the particles age, it ages to this blue color. Now you can go back inside of your Portal Geo, and on this shader node, adjust these variables to whatever color you'd like. So a bright green or a cold blue. And then you can also adjust the brightness. If you want this very dim, you can set that to 0.1. Or if you want it extremely bright, you can set this to 5. And it's really just down to personal preference. And you can just keep messing around with these until you find something that you like. And a few things to note is the parameters that really affect the way that your portal looks will be covered at our blog post, and you can go check that out. But as you can see, it's a very solid ring, and to change that you can adjust the number of particles that are emitted, or you can change your resample maximum segments. So a value of 100 will put a much lower number of points that it's emitting from, so it'll look quite sparse. So thanks for watching. That's it for this tutorial. And if you would like further information on any of the VEX code, that will be at our blog post on our website, as well as any new releases that we may have. And if you would like us to recreate any effect from any movie, then please comment down below and we'll get to that. So once again, thanks for watching.